When you look at a really complex piece of architecture, do you ever wonder how it all just works? Well, designing a drug is a lot like that. It's like a molecular puzzle. You start with a basic foundation, you add very specific features to make it functional, and even tiny little changes can completely alter the purpose of the whole structure. So today, we're going to be the architects. We're going to deconstruct the blueprint for one of the most famous classes of anxiety medications and figure out exactly what makes them tick.
So that brings us to the big question, right? How does a small collection of atoms, just arranged in a particular shape, get this incredible power to interact with our brain chemistry and actually create a feeling of calm? Well, I can tell you it's not magic. It's a set of very specific, very clever design rules. And today, we're going to uncover them together. So here's our game plan. First, we're going to look at the basic blueprint of all benzodiazepines. Then we'll get into the strict rules that a molecule has to follow to have any effect at all. We'll also check out a really clever trick called the pro-drug strategy, and you'll see the massive impact of changing just one single atom. And finally, we'll put it all together to see how these drugs are categorized. All right, let's dive right in. Section 1, the blueprint. Every great building has to start with a solid foundation, a frame. And in the world of these anxiety medications, or anxiolytics, that core frame is something called a diazepine. Let's see what that actually is. So what in the world is a diazepine? It sounds complicated, but it's actually pretty simple. All it is a 7-sided ring of atoms, and inside that ring, 2 of them are nitrogen atoms. That's it. This is our fundamental building block, the simple, bare-bones frame that we're going to build everything else on top of. But just any old frame isn't enough, right? We need a specific model of that frame. And for what we're talking about, we're focused on the 1,4-benzodiazepine. This is the specific arrangement that chemists figured out was the perfect starting point, the lead compound, for creating drugs that calm anxiety. So this is our real blueprint. Okay, so a blueprint by itself doesn't really do anything. We have to add the functional parts. So what are the strict architectural rules that turn this totally inactive frame into a molecule that can actually do its job and reduce anxiety? Rule number 1 is an absolute deal breaker. Within this structure, there has to be a double bond between the atoms at positions 4 and 5. It is completely non-negotiable. If you take that away, the molecule loses all of its ability to reduce anxiety. It's like pulling a critical support beam out of a building. The whole thing just functionally collapses. And that brings us to rule number 2. The molecule also needs something called a carbonyl group. That's the carbon-oxygen double bond, which in this case is a ketone. And again, this isn't just for decoration. It is another absolutely essential component for the drug to have any effect in the body. So you gotta be asking, why? Why is this one little group of atoms so important? What's its secret? Well, here's the brilliant part. That ketone group helps create a new feature called an amide group. And this amide group is incredibly stable because of something called resonance. Now think of resonance kind of like a musician holding a perfect note. The energy is spread out, it's sustained. This lets the electrons in the molecule spread out, which makes the entire structure way more stable and strong. And it's that stability that allows the drug to effectively dock with its target in the brain. Now we get to a really clever bit of molecular engineering. What if you could design a drug that only becomes active after it's already inside the body? Well, that's what the prodrug strategy is all about. A prodrug is basically a molecular Trojan horse. You deliver it to the body in an inactive form, and then your body's own metabolism does the final bit of construction, converting it into the active drug right where it needs to be. It's genius. Chlordiazepoxide is the perfect example of this. If you look at its original structure, it's missing that essential ketone group we were just talking about. But once it gets inside the body, our metabolism acts like a tiny construction crew, it adds that ketone, and bam, the molecule becomes active. It's just a brilliant strategy for improving how a drug gets absorbed or delivered. So we've seen the big overarching rules, but now we get to what I think is the most fascinating part of medicinal chemistry. How one single, tiny atomic change can have these huge, dramatic consequences for how a drug behaves. Okay, this right here is the crucial point. On the left, you've got your standard benzodiazepine. It lasts a long time and it gets into the brain pretty easily. But on the right, you add just one tiny little hydroxyl group. That's an oxygen and a hydrogen atom at a very specific spot. And everything changes. The drug becomes more hydrophilic, which literally just means water-loving. And because our brain is protected by a fatty barrier, this new water-loving molecule has a much harder time getting across. The result? A much shorter, faster-acting drug. It's incredible. One single atom completely changes how the drug works in your body.
So now that we have our architectural rules, we can finally see how chemists and doctors actually categorize these drugs. It's not random, it all comes back to the structure.
And look at that, it all makes sense now. The major classes are named after the exact features we just talked about. You have the 2 keto drugs. Yep, those are the ones with the essential ketone group from rule number 2. Then you have the 3 hydroxy drugs. Those are the ones with that single atom change that makes them short-acting. The name literally tells you its architecture. It's a completely logical system based entirely on that molecular blueprint.
This really brings it all home. This quote is the core message from the source material we've been looking at, and it's the key takeaway for us. To really understand how these medications work, you have to connect the name of the drug to its class, and then connect that class to its unique molecular shape. The structure is the story.
So, let's end on this thought. We've seen just how meticulously these molecules are designed, and how a single atom can completely redefine a drug's entire behavior. It really makes you wonder, as our ability to manipulate molecules gets even more precise, what kind of targeted, personalized medicines are just over the horizon? What will the next generation of these molecular blueprints even look like?